You know, it's pretty wild to think that the incredible power of a single, simple proton transfer can completely change the entire nature of a chemical reaction. It's honestly like a microscopic game of tag, and it literally dictates how our universe operates on a molecular level. So welcome to this explainer. Today, we are absolutely mastering Brønsted-Lowry acids and bases. We're going to visualize exactly who gives protons, who takes them, and how mastering this invisible subatomic exchange is going to win you those crucial marks on your O-level chemistry exams.
Okay, let's dive right into this. Here is our roadmap for today. We're starting off with the power of protons, then we'll establish the Arrhenius baseline before moving up to the Brønsted-Lowry upgrade. After that, we're going to track some proton transfers step by step, figure out how to avoid common exam traps, and then wrap it all up with a recap and some final tips.
All right, kicking things off with Section 1, the power of protons, and this idea of a subatomic exchange.
Seriously, we've got to stop looking at chemical reactions like they're just static, dead letters printed in a textbook. Instead, try to see them as these dynamic, interactive exchanges. The absolute secret to predicting reactions really just comes down to one core question: who gives and who takes? Whether we're looking at massive industrial manufacturing, like, say, producing fertilizer, or the delicate biological systems digesting your lunch right this very second, understanding a reaction relies on tracking this exact subatomic exchange. Basically, if you can follow the proton, you can understand the chemistry.
Moving right along to Section 2, the Arrhenius baseline. This is our aqueous foundation.
So, before we look at the modern model, we need to establish exactly how early chemists defined these fundamental reactions. An Arrhenius acid is strictly defined as a substance that releases hydrogen ions, which we've labeled here as H+, when it's placed in water. Conversely, an Arrhenius base releases hydroxide ions, labeled as OH-. Now take a look at that bold text, highlighting the words "in water." That right there, that is the major limitation of this baseline model. It literally only works in an aqueous solution. If there's no water, there's no Arrhenius acid or base.
Let's actually look at a step-by-step flowchart of this in action using hydrochloric acid. Over in Step 1 on the left, HCl is added to our aqueous water environment. Moving over to Step 2, the HCl dissociates. Now, follow the arrows right into Step 3. You can clearly see the physical release of that H+ ion into the water, separating entirely from the Cl- ion. But again, keep in mind this entire process is trapped inside that beaker of water.
Which brings us to Section 3, the Brønsted-Lowry upgrade. We are going beyond the beaker.
Well, science rarely settles, right? Chemists realized they needed a more elegant, universal solution to overcome those strict aqueous limitations. Now, what's really interesting about this split-screen comparison we're looking at is the contrast. Over on the left, our Arrhenius model is completely boxed in by its need for an aqueous environment. But look over at the right side. The Brønsted-Lowry model completely breaks that boundary. It applies to literally any environment. It simply asks, is it proton being donated, or is a proton being accepted? This brilliantly illustrates how our understanding of chemistry expanded way beyond just water.
So let's explicitly define the core variables of this new model so you can visualize the mechanics perfectly. A Brønsted-Lowry acid is defined solely as a proton donor, and a Brønsted-Lowry base, that's defined as a proton acceptor. Boom, that's it. The acid gives the proton, and the base takes the proton. It is a direct subatomic transaction.
Let's put this into practice in Section 4, tracking proton transfers, by looking at the microscopic vector flow.
Okay, let's zoom way in to the molecular level and track the actual flow here. In Step 1, hydrogen chloride gas reacts with liquid water. Now guide your eye along that bright vector arrow there in Step 2. See that? It shows the H+ proton physically transferring from the HCl molecule directly over to the H2O molecule. Because HCl is the donor, it's our acid, and by accepting that incoming proton, water is acting precisely as our Brønsted-Lowry base. Finally, in Step 3, this transfer successfully forms our new products, hydronium ions and chloride ions.
Now, watch what happens when we flip the script a bit with ammonia. Step 1, NH3 gas reacts with liquid water, but look closely at the direction of the arrow in Step 2 this time. The physical flow is completely reversed. The H+ proton is leaving the water molecule and attaching itself to the ammonia. Because water is donating the proton here, it's acting as the acid. Ammonia takes it, acting as the base, which leaves us in Step 3 with ammonium and hydroxide ions.
Okay, pause right here because this brings us to a highly testable term you absolutely need to know: amphoteric. Think about what we just saw. We literally just watched water accept a proton in our first equation, acting as a base. Then we watched it turn around and donate a proton in our second equation, acting as an acid.
A substance that can act as both an acid and a base earns this special label, amphoteric. Water is the classic textbook example you've got to remember for your exams.
All right, let's map out these structural relationships. This table does a great job of visualizing what we call conjugate acid-base pairs. Look at the rows we've got, HCl and Cl-, H2O and OH-, NH4+, and NH3. Now check out that difference column on the far right. Notice how every single pair differs by exactly one H+ proton? That right there is the visual signature of a conjugate pair. When you are prepping for your exams, keep an eye out for molecules that look almost identical, except one has an extra hydrogen proton.
Moving into Section 5, avoiding common exam traps, we are setting up some boundary markers. Look, I don't want you losing easy points over silly things, so it's time to place some clear boundary markers to protect you from the most common misconceptions. Trap number 1, assuming that all acids and bases must visually contain an H+ or OH- ion right there in their written formula. Remember, Brønsted-Lowry is universally about the transfer of the proton, not just static ions sitting there. Trap number 2, assuming all reactions must occur in water. As we've clearly mapped out, this model works perfectly in non-aqueous, gas phase, or even biological systems too. Don't let these misconceptions fence you in on test day.
And finally, Section 6, recap and final tips for nailing that O-level exam. Let's consolidate everything we've talked about dynamically to make sure you crush your exam. Ready for a rapid-fire recap? Here we go. 1. Arrhenius is strictly about releasing H+ or OH- specifically in water. 2. Brønsted-Lowry is a direct proton donor and acceptor transaction. 3. This expanded model frees us, applying way beyond just aqueous solutions. 4. Conjugate pairs always, mathematically, differ by exactly one proton. And 5. Water is amphoteric, powerfully playing the role of both acid and base depending on the flow of the reaction.
Now here is your ultimate call to action for your exam strategy. When you're writing out your answers, you must clearly identify whether you're using the Arrhenius or the Brønsted-Lowry definitions. Seriously, do not leave the examiner guessing. And always use examples. Draw the molecules out, draw the vector arrows showing the physical proton transfer, and practice explicitly identifying those conjugate pairs. Doing that is how you secure every single full mark available.
Before we wrap up this explainer, I want to leave you with a thought to provoke your curiosity just a bit beyond the textbook. Look around you right now. You are surrounded by incredibly complex chemistry, from the air you are breathing to the food digesting in your stomach. Now that you actually know the rules of the game, where else in the world around you do you think silent, invisible proton transfers are occurring at this very second, driving the systems of life? Keep observing, keep questioning, and I'll catch you in the next explainer.